Our last two examples deal with solving absolute value equations with polynomial functions contained inside the absolute value bars. Recall that in order to solve these, we set up two different equations. In the first case, we simply drop the absolute value bars, and in the second case, we drop the absolute value bars and make the answer or the value on the right-hand side equal to its opposite. From there, what we'll do is subtract 35 to the other side and look at solving both equations. X squared minus 2x minus 35 will factor as x minus 7 times the quantity x plus 5. Set equal to 0, we can solve by considering x minus 7 equal to 0 and x plus 5 equal to 0, which will give us x equals 7 and negative 5 as two of our solutions. The expression that we have on the right, x squared minus 2x plus 35, actually turns out to be prime, meaning we can't factor that using real numbers. So what we'll have to do is apply the quadratic equation, which means x will be equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2 times a. Or in this case, that will be positive 2 plus or minus the square root of negative 2 squared minus 4 times 1 times 35 all over 2. If we evaluate the expression under the radical, this ends up becoming the square root of negative 136. Referring back to how this problem was originally worded, we're looking for real solutions. And if we're considering real numbers, the square root of 136 doesn't exist. We can't take the square root of negative numbers unless we start introducing complex numbers or imaginary numbers. That means for our purposes now, this doesn't lead to a solution, and our full solution is simply x equals 7 or x equals negative 5. We'll start off example 18 in exactly the same way. First dropping the absolute value bars, and then setting up a second equation where we drop the absolute value bars, but set the expression on the opposite side equal to its opposite. Negative 6 and 6 will cancel with our first equation, leaving us with x squared plus 4x is equal to 0. We have a greatest common factor of x which we can pull out, leaving us with x times the quantity x plus 4 is equal to 0, meaning x equals 0 and negative 4 are possible solutions. Scratch that. I was jumping ahead and thinking through the other half of this problem. What we would actually do in this case would be subtract 6 to both sides, which would give us x squared plus 4x minus 12 is equal to 0. And in the second equation, we would add 6 to the other side, and that's where those 6's cancel out. So for our first equation, this would end up factoring as x plus 6 times x minus 2, which is equal to 0, which would give us solutions of negative 6 and positive 2. With our second equation, now that those 6's have canceled out, we would have x squared plus 4x is equal to 0. Here we would factor out that common x, and now we would actually arrive at those two solutions that I mistakenly came up with at first. In this case, both the first equation, where we just drop the absolute value bars, and the second equation, where we set what was inside those absolute value bars equal to the opposite of the other side of the equation. Both of those lead to solutions, meaning our full solution in this case is a list of 4 values: -6, +2, 0, and -4, all of which would be solutions to that original equation.